And we're going to look at static and dynamic friction. In particular, do a mini lab where we'll calculate the coefficients of static and dynamic friction. And you can pause this or come back to this particular slide. There's a summary of what you're going to do, and very importantly, what you're going to submit, what you need to complete as you do the mini lab. But we're going to go through the instructions a little bit at a time, and the ramp with the block on, as you lift it, the block doesn't move if the angle of the ramp to the horizontal to the table isn't great enough. And look at the variables here, and in red we've got the force of friction equals the coefficient of static friction mu s, and then the normal force Fn. If we look at the second diagram here, as you lift the ramp, it just starts to move, and that's where you will do your measurement to get the angle. And the first thing we're going to do is draw the free body diagram. And we have it here with the normal force perpendicular to the angle of the ramp, the force of friction in opposition to the forward motion of the downhill motion of the mass, and then the force of gravity acting on the block going vertically downwards. And so we're going to create a force vector diagram from this, and as we do that, we will want to know the angle, and in order to get the angle you will measure the height at which it just starts moving from the bottom of the ramp down to the horizontal table. And so you now have the height of the ramp, and you can measure the slope from the table up to the point at which on the meter stick when it just starts moving. And so the sine of the angle is opposite over hypotenuse, and you can work that out. There's an example given here. And then we'll have the force vector diagram from that, and as you will see, we've just added it here to the free body diagram, and we're extending the normal force equal and opposite direction. So we've got a measurement of it with the downhill force and an angle, but the one or two things that we know, the angle, and we also know the force of gravity acting on the object. Two reasons: if we know its mass and then the force of gravity, multiply them together, or we can use a spring balance to get f of g. And so there it is, a little bit clearer here. And we know that f of n equals the force of gravity cosine of the angle, and the downhill force is the sine of the angle times the force of gravity. So then we have f of the downhill force, and we have the normal force. And going back to the equation that we had, we know that the coefficient of static friction equals the downhill force Ff over the normal force Fn. And the mg's cancel out here, and so you get sine over cos, which equals the tan of the angle, and so we can actually get the numerical value for the coefficient, which doesn't have any units. And going on to part 2, for the coefficient of dynamic friction, again pause, because a different set of things that you will submit, but we'll go through the actual instructions, the top part of that, part by part. And so we're going to pull the same block along a horizontal ramp. So the ramp is the same ramp and the same block used on the horizontal table. And you're using a spring balance to measure the pulling force used to maintain a constant velocity, no acceleration here, and complete a number of trials to do this. Measure the mass of the block. In fact, here you'll measure the force of gravity acting on the block directly with a spring balance and do a number of trials to get your answer for that. So we're pulling the block, but make sure you do it horizontally and maintain a constant velocity. Then we can draw the free body diagram of the block with the pulling force coming out to the left, and then the force of friction. And once it's moving and you've got a constant force, you have exceeded the force of friction. And then the normal force again, perpendicular to the surface, and here you've got the force of gravity going directly downwards or acting on the block. And then the force vector diagram is very, very similar. And here we've got the red formula at the bottom. The force of friction equals the coefficient of dynamic friction multiplied by the normal force. And so you've got the calculations in there. We know m times g, or indeed the force on the block that you're reading off the spring balance when it's held vertically. And so you're putting in your numbers. You've got the force of gravity acting on the block again. You've got your force of gravity equal to your normal force here. And your, with a constant velocity, your pulling force is equal to your force of friction. And so we get the calculation for mu d, the force, the coefficient of dynamic friction, being 0.14. And then you can pause this one to look at them. In the top one, add your results here for your static coefficient of static friction and your coefficient for dynamic friction in that top area, and then compare it to two other mediums. And it says name the materials that your block and your ramp were made out of. And some of them are quite sort of surprising, and you'll be asked a bit later what you notice about the two coefficients in the columns. And we're also going to do a calculation, actually from the start of class. We want to calculate the force of friction on the block and the diagram. Here we've got an acceleration, we've got an angle, and we know the mass of the block. So where do you start? Pretty much where you start on all of these, we're going to draw a free body diagram. And again, you've got your normal force perpendicular to the slope of the ramp. You've got the force of friction and the force of gravity acting on the block. and we know the angle, so the sine of 30 is the downhill force over the force of gravity acting on the block, and you can calculate the number of newtons hit there, 24.5 at the bottom right hand side. And the force of friction equals the downhill force minus the net force. And so you've worked the net force, which is mass times acceleration. And so we've just worked out the downhill force and the force of friction. Subtract net force from the downhill force and you get your 14.5 newtons. Some are they everyday examples? Well, winter examples here. And just pause here and check out the free body diagrams and the force vector diagrams that you've got for both a skier and a snowboarder. And then a reminder of what friction is. When you look in microscopic detail of here, you've got a crate on top of a surface. There's no flat surface that it's sitting on. There's no flat bottom to the crate, and it's those sort of undulating, when you look at the microscopic level, that are causing the friction. And if you look at the diagram on the right, you've got here a tip that looks more like an anvil, but a tip of a very fine metal needle that's actually made out of a very thin, but it doesn't go down to one atom, one molecule. And then you can see the distortions that take place as you're dragging the very thin tip of the probe across a surface. Little activity about good friction, bad friction, and some of this will be review. If it's helpful, it's good friction. If it's unhelpful, it's going to be bad. So read each of these in turn and look at the diagram and decide the part that is being asked about. So the tires for number one on the moving bike, nothing about the pedals, nothing about anything else. And you also have a table here that you can fill in. So describing the friction that's involved. Is it good friction or bad friction? You're deciding. And name the two surfaces, the materials that are involved in the friction there. And also, here's a small, fairly simple experiment to do at home. But look at the last but 3 lines. The situation is important for drivers, especially after a light rain shower. So it's just worth looking at that and coming up with what you've got. Something that I heard described once as Florida ice. And just to finish, some answers. I'm not going to dwell on that. You can, if you want to read through it, to check what your answers were. But very many thanks to Washington International School of Science and Mr. Jollimore's physics class. Thank you.